Okay, section 2B, acids and bases. So as always, whoop, there's your learning outcome. In this case, it's one, but it's quite a big one. Okay, now just to give you a little bit of context with what's happening here, I mean, acid-base chemistry is an important part of chemistry. There's no doubt about that. But I also want to put this into some perspective here because last week we looked at polyatomic ions, and I basically said to you, look, just kind of take it for granted that these polyatomic ions exist. Um, they actually arise as the result of acid-base chemistry. And so I want you to keep that in mind as we're going through this. Okay, so it's not just acid and base chemistry we're doing here, it's also uh, putting that piece in the puzzle about polyatomic ions. Now, acid and base chemistry, now let's get on with the acids and bases. So acid and base chemistry is really all about H+, which is why I've got that title there. Or you can say it that way, acid and base chemistry is H plus chemistry. Now, because of the importance of H plus, we've got to think a little bit about what H plus actually is. Now, if you look at the periodic table, you'll see that hydrogen, atomic number 1, it has 1 proton and it has 1 electron. So the fact that we're thinking about H plus obviously means that the hydrogen in this case has lost its electron and the only thing left is a proton. So H plus is a proton. That's the way it is. Now I know there are some isotopes of hydrogen that have neutrons. In fact, there's two of them, deuterium and tritium, but really um, the amounts in nature are minor and we can forget about that. So for us, always, in fact, when we're thinking about acid and base chemistry, all chemists think this way. H plus is a proton. Okay, now the next important point about acid and base chemistry is to keep in mind that protons can't exist solely by themselves. They're not just sitting out there somewhere. They've actually got to kind of be on something. So this is a really important idea because what this means is we conceptualize this idea of a proton, that is a H plus, but in reality, it's always on something. Okay, so just be aware of that. Now, if it's always on something, then something can, when you think about it, that thing can donate a proton, but of course then something has to be available to accept it. You can't have one without the other because they can't exist on just by themselves, protons that is. So sometimes it's actually better to think about acids and bases as thinking of them being donors and acceptors. And that kind of implies a mutual arrangement. I mean, clearly, if I use the word donor um, in everyday life, it implies I've donated something to someone, right? And so therefore, whoever that someone is has therefore become the acceptor. They must have accepted it. There's a mutual arrangement going on there. And that's really what acid and base chemistry is all about in a nutshell. It's the donation and acceptance of protons. So the next thing I want you to realize is that when you're looking at a molecule, as you know, molecules are not charged. Molecules are covalent compounds comprising atoms, and atoms themselves are not charged. Then what that means is if a molecule donates a proton to something, then the bit that's left over has to be negatively charged. That is, it has to be an anion, like this one here. So when we look at this is an acid, hydrochloric acid, it can donate a proton. I've written it like this here. And then what's left over, of course, is Cl minus. And of course, if you just add the plus and the minus together overall. The charge is 0 again. Now, notice what I've done here, by the way. I've drawn a H plus by itself, but H plus by itself never exists. Am I wrong? Not really, because people know that H plus by itself doesn't exist, and what I'm trying to do is get across an idea. Remember, at the end of the day, all formulae, all equations are simply representations of what's going on. They can't represent everything, and in this case, all I wanted to represent is that when this molecule here gives up H plus, the remaining part must be Cl minus. Now, obviously, if a molecule then accepts a proton, so here's our proton here, so it could have come from HCl, for example. This molecule here, by definition, all molecules have 0 charge, then it's accepted a H plus charged particle here, if you like, and of course what results is this compound here, which is NH4 plus, where this hydrogen, of course, now it's got 4 hydrogens, but overall this thing is got a plus charge on it. Now, technically, you shouldn't really refer to this guy here as a molecule, because the word molecule normally implies that the thing has no charge. Not always, but normally, right? So we're actually going to use another term when we're talking about things like this that have charges on them. And this one here is got more than one atom, so it's polyatomic, as you've already encountered previously, and it has a charge on it, so therefore it's an ion, so this thing is a polyatomic ion. In this case, of course, it's a polyatomic cation. So that's just getting our heads around protons. Now let's look at acid and base chemistry in an absolute nutshell here. So an acid, by definition, is a proton donor, right? Now think about this. If a proton is H plus, then all acids must therefore contain H. They must contain hydrogen, right? So all acids have that common feature. Now, having said that, just be careful here, because it doesn't necessarily mean that all molecules that contain hydrogen are acids. So for example, we looked at CH4, that compound's called methane, CH4. It's not an acid, even though it contains hydrogen. So acids have this kind of special property that they contain hydrogen and then can donate hydrogen as a hydrogen ion, that is a H plus ion. So what's happening there? Well, when an acid then donates H plus, of course, that hydrogen originally had its own electron associated with it, and that electron is left behind. So if the acid is neutrally charged and it's then the H plus is left behind its electron, the thing that's left over must then be negatively charged. Now, a common feature of all acids is that they can donate protons to water. So here's an example here with a formula where we've got our friend HCl here. There's our covalent bond there. If you'd like, in fact, not if you like, it is the case. This hydrogen is in effect donating one of its electrons to this bond. This chlorine is donating the other one. And then when HCl reacts with water here, it actually gives up the H plus. So in fact, if I get my pen here, it gives up this bit, of course. And of course, when it does so, that's now H plus. Its electron is left behind here, and now of course you have Cl minus. There it is there. And And of course, that H plus has been added to the H2O, and you end up with H3O plus. Now, this might seem a little bit peculiar to you that this compound here, HCl, hydrogen chloride as it's called, it's actually a gas. And I did explain that to you in a previous lecture. And it's, if you like, another way to draw it would be like this, where we've got a HCl like this, and this is our covalent bond here corresponding to these two electrons. Now, HCl gas, if you bubble that through water, what happens is it actually splits into, well, it donates a H plus to water, and it becomes H3O plus, and then what's left over is the Cl minus there. Now, over in this diagram here, we've got that occurring in a kind of odd way, I guess, because you look here, I've stressed to you that there's no such thing as H plus by itself, but chemists often do this. They've actually written this here as H plus AQ, which is really meaning that, well, in fact, all that has happened there. So where you see H plus there, I hope you can see it's actually H, this is actually a H water H2O molecule with a H plus on it there. So this is H3O plus, there's another H3O plus, there's another H3O plus. And of course, overall, the material that you get is neutrally charged. Okay, now you're probably wondering about bases. So because if something's donating a proton, something has to accept a proton. These, by definition, are bases, and a common one is this one here, hydroxide ion. Now, I didn't make it explicit last week, but you did. This is actually listed in your periodic table and other information, and this is a polyatomic ion. Right, so you can see it's got more than one atom. They're both non-metals, which is what you need for these polyatomic ions, and it's indeed an ion because it's got a 1 minus charge there. So these are common, these hydroxide ion bases. Now, hydroxide ions can't exist by themselves because they would be just all negatively charged, and if such a substance existed, it would just blow itself apart because like charges repel. So there's a metal ion that goes along with it, a so-called counter ion, so opposite in charge, that then allows the substance to exist as a compound, and they're normally metal ion hydroxides of groups 1 and 2. Now, if you look at your periodic table, you'll see that in group 1, and remember, elements in groups behave in the same way. In group 1, you've got lithium, sodium, my goodness me, talk about a brain explosion, lithium, sodium, potassium, rubidium, cesium, francium, right? So, and they all have a valence of 1. They all tend to give up 1 electron, and so it's not surprising there that these substances, this is lithium hydroxide, right? This is actually Li plus OH minus, and that makes great sense. Sodium's in the same group, so it's Na plus OH minus. Now, if you look at calcium in the periodic table, you see it's in group 2, and it's not surprising then that it's Ca2 plus OH minus. And remember, these are ionic compounds. The charges aren't written, they're implied, which does make it, as I've said before, a little bit confusing. By the way, if you're distracted by this, little GIF just here. This is someone doing a titration where they're adding acid and base together to the point where they actually cancel each other out. And the solution is basically salty water. More on that in a little while. In fact, right now. So what have we got here? Well, if you add an acid and a base together, where the base is a hydroxide base, there are other kinds, but generally, well, often they're a hydroxide base, you end up with a salt and water. Let's see how that works. So here we've got HCl, that's an acid, right? That's in solution, so you can think of it as being like this stuff over here. And you're adding sodium hydroxide, that's in solution as well. And what's happening there is, let's draw some things in here. We've got Na plus, OH minus, this H plus here. You can think of this at the moment as Cl minus, even though it's a covalent compound, it'll do. This H plus adds to this OH minus, and you get H2O. Add them together. H plus plus OH minus gives H2O. So there's our water. What's left over, because nothing else happens, you end up with Na plus Cl minus. There it is there. Right, remember, that's actually this. And it's, at the moment it's in solution. So the bottom line is this: if you add precisely equal amounts of those two compounds together, HCl and NaOH, you end up with salty water. If you then evaporate the water off, you end up with solid sodium chloride, the ionic compound. Okay, now that actual idea applies to anything where you're adding an acid, any acid, it doesn't matter, plus a base. So here's another example. We've got HF, that's an acid. We've got lithium hydroxide in this case, and we end up with water. There it is again. There's our H plus, our OH minus there. We end up with H2O. And of course, lithium fluoride is actually Li plus F minus. This one here, this one's a little bit different because this is magnesium hydroxide and it's got two hydroxide ions for each magnesium ion. This is Mg2 plus. Look at your periodic table, you'll see that it's in group 2. This is 2 lots of OH minus. So you actually need 2 lots of this stuff. Remember the stuff last week about coefficients? You need 2 lots of this stuff to cancel out 1 lot of this stuff here, right? Because there's 2 lots of OH minus in it. And of course, when you do that, you end up with 2 lots of water and 1 compound here that's magnesium 2 plus and 2 lots of Cl minus. So, okay, my last point here. Now these atoms here, these acids here are 2 atom compounds to start with, right? So these are binary acids, binary meaning 2, right? One of the atoms, of course, has to be hydrogen and then something else that will then be happy enough to let that hydrogen go as H plus. So all these binary acids here, they'll obviously have hydrogen in them, otherwise they can't give a proton, and then they'll have some other non-metal attached to them. It's got to be a covalent compound to start with, right? And generally or commonly they're from group 17. Now if you look at group 17, it's right next to the noble gas family. Now, even though that's the case, that you have these binary acids, there is one other sort, and that's where we start thinking about polyatomic ions. So this other group of acids are called the oxyacids. Now, obviously, they're called oxyacids because they contain oxygen, but they still do the same thing that any other acid does, that is, they donate protons. Now, these are actually listed in the SCI 105 periodic table and other information. So you don't really have to memorize them. Just make sure you can locate them there. Okay, so let's have a look at an example. This one here is nitric acid, HNO3. Now, before we get into this, notice we've got non-metal, non-metal, non-metal. It is a molecule. It's joined together by covalent bonds. There it is there. Now, in this case, for the Lewis structure, what I've done is drawn some of those bonds in as lines, right? Each one representing a covalent bond, of course, and one covalent bond there as 2 dots for the electrons. So that's nitric acid, and there's only one possible atom that's going to be given up as a proton, of course, and it's this guy here. So this will leave as a proton, and it will leave its electron behind. There it is there, and I'll show you in a minute that you end up with NO3 1-. Here's another one, and of course when you do end up with NO3 1- here, this is your polyatomic ion. Here's another one. This is acetic acid. Again, you don't have to remember these. They're in your periodic table. Obviously, this is the candidate here, this guy, and that one leaves. And here's another one, nitrous acid. Notice the difference in the name here. This is nitric. This is nitrous acid. There it is. Now, this one's a little bit unusual in that there's 2 potential candidates here where the protons can leave. By the way, if we go up here and just look at acetic acid for a moment, you'll see that this part of the molecule here has got hydrogens with it as well, but they remain firmly attached to this carbon. None of those leave. The only hydrogen that leaves as a proton is that guy there, right? Notice, by the way, this formula is written like this, which really translates into the Lewis structure as this. Okay, now we go down here to carbonic acid. In this case, either of those 2 hydrogens can leave. Now, I hope what you can see, by the way, is that there's a common feature going on here. Basically, for something to act as an acid, the H has to be attached to an oxygen, has to be attached to something. So H, if we're looking at this H here, has to be attached to an oxygen. This oxygen here has to be attached to something, and that something has to be attached to something like an oxygen double bond. Here it is here again with acetic acid. That H there is attached to an oxygen, is attached to something, is attached to an oxygen double bond there. Notice that those H's there in acetic acid, they're not attached in the same fashion. It's this arrangement, this type of arrangement here, that actually makes things acidic and allows them to donate protons. So in this molecule here, now getting back to carbonic acid, you can see you've got that arrangement there, and you can also see you've got that arrangement going this way as well. So both those hydrogens can be donated as protons. So that kind of acid, where it can donate more than 1 proton, is called a polyprotic acid. Here's another one. Here's sulfuric acid. Now, what have we got here? Look, there it is. In this case, it's not a carbon or a nitrogen, it's a sulfur, but we've got that similar arrangement there and that similar arrangement there. So sulfuric acid is actually a polyprotic acid as well. Now, this one's interesting because this occurs a lot in biological systems and in things like DNA and RNA, etc., which I'm sure you've heard of. So this guy here is actually, it's got that arrangement there, so I can give up this as a proton. Similarly here, so I can give up this as a proton, and similarly here, it can give up this as a proton. So this acid is a polyprotic acid as well, but it's actually not a diprotic acid like carbonic acid and sulfuric acid. It is a triprotic acid. It can give up 3 protons. And of course, when it does that, it gets progressively more negative. If this compound here, phosphoric acid, gives up 1 proton, then it leaves 1 electron behind and it becomes, you've got 1 minus sign. If it gives up 2 protons, it becomes 2 minus, and if it gives up 3 protons, it becomes 3 minus. Now, even though oxyacids are a little bit different to the binary acids that we just looked at, they always they do the same kind of thing that any acid does. That is, they'll react with a base, and when it comes to hydroxide bases like this one here, sodium hydroxide, which by the way is a common component in stuff like drain cleaner, sodium hydroxide here plus this acid, this one's acetic acid. Which proton's given up? It's that guy there. We've got a proton plus OH. Remember, this is OH minus Na plus because this is a polyatomic ion here. And of course, you end up with water and you end up with a salt. There it is. There's our ionic compound, our salt, and it is CH3COO minus Na plus because this thing gave up its proton here. Now, with all ionic compounds, they have similar features, as I tried to stress last week with sodium chloride, right? Essentially, the way in which they fit together as a compound is anions will be surrounded by cations, cations by anions, and they're going to form a crystalline high melting point substance. And this compound, its actual name is sodium acetate. Sodium acetate. I'll talk more about nomenclature later. Sodium acetate, it is definitely a high melting point crystalline solid. And this is a beautiful example of some crystals forming where you've just added sodium hydroxide and acetic acid together. Now, just a little bit extra on formulae because you can get a little bit confused here, particularly when you're just starting out. One of the problems you often have in chemistry is that people will write down formulae for substances in different ways, and it tends to be kind of discipline specific almost. So, for example, this formula here, this one here, is well, actually, let's first of all get this dot 3H2O out the way first before I talk about what's going on here. So that dot 3H2O means that for every formula unit of this, remember this is an ionic compound, you've got to call this a formula unit. For every formula unit of this, it has 3 water molecules associated with it. Now, people have made the stuff, right? They've made the material like this. All of this is happening in water, as you can see, and sometimes you can't get all the water out of the system, but you can actually measure how much water is in there. And in this case, for this particular product here, which is the trihydrate form, tri means 3, hydrate water, So for this compound here, this has got 3 water molecules associated with it. You need to know that when you're actually measuring this stuff out, because it's got extra water in it that you've got to take into account. More on that one later, but for the moment, I just thought I'd point out the 3. Now, getting back to this issue with formulae, it's getting a bit messy here. Getting back to this issue with formulae, you could write the formula for this stuff as for this stuff as this, right? So in this one, you're really just saying how many atoms are present in that formula unit, um, and you're not particularly concerned about anything to do with the structure of it, right? So you've got 2 carbons, there they are, there and there, right? So you just put 2 carbons there, etc., etc. Now, as I said before, it gets a little bit discipline specific here. So me, with my background in biochemistry, I would find it absolutely bizarre that you would write the formula this way. I would want to have it like this, because it actually tells you something about the structure of it, right? This here is giving me an idea that it's actually this, which is what I'm generally more interested in. Okay, so you don't really have to remember any of this stuff. I'm just pointing this out because it's easy to start looking through this and going, well, hang on, I've been told X and it's kind of changed, etc. Well, I'm just giving you a heads up that sometimes things aren't entirely consistent. Okay, so let's just run through all this again. So here's some oxyacids. Here's some oxyacids here. We've already encountered these guys. By now you should be able to recognize where those hydrogens are that are going to drop off as protons. So let's go through it. So to get them to drop off, you've actually got to get these protons to drop onto something. That is, they've got to drop onto a base. And the conceptually easy way to think about it is they're going to drop onto something like sodium hydroxide, a nice simple hydroxide base here. Generically, you could write it like this, HA, so that H is corresponding to that hydrogen there, and then you don't really care too much about the counter ion, but generally what will happen is that H adds to that OH minus. It needs a counter ion for this OH minus, we've just called it X here, and of course you end up with a salt, there it is there, plus water. So let's just go through this then. So there's the nitric acid form. That's after it's lost its proton to a base. Now notice the change. Now we'll do a little bit on nomenclature. Notice the name here. This is nitric acid. The name of this thing is nitrate ion. Notice how the name changes, and it's NO3 1 minus. That one there is nitrite ion. Now for phosphoric acid, so they're monoprotic acids, nitrate and nitrite, but for phosphoric acid, of course, it's a polyprotic acid, so it can lose 1 proton, in which case it becomes that stuff, 2 protons, 3 protons. And you'll notice here, these are all polyatomic ions. Now, you know where these have come from, these polyatomic ions, so just be aware that all these are also listed in your periodic table and other information, so you don't have to memorize them. Okay, there's something for you to think about there. Okay, now we've done quite a few anionic polyatomic ions. There is a couple of um, um, polyatomic cations that we want to look at. Now, one of them we've actually already looked at in a way, because remember we did water. So when water has a proton added to it, it becomes H3O plus. That particular polyatomic ion is called hydronium ion, and clearly it's a cation, it's positively charged. One of the frequent ones you're going to come across is ammonia. Now, ammonia can act as a base, and when it acts as a base, it actually picks up a proton and becomes NH4 plus, as I've written there, ammonium ion. So here's an example. If ammonia, and there it is there, NH3, is going to act as a base, it's going to have to pick up a proton. On goes the proton, and you end up with NH4 plus. Like that, there's ammonium ion, and of course what's left over from this acid is Cl minus. Now notice what's happened here. This is an acid plus a base, but now it's not a salt plus water. That only occurs when they're hydroxide bases. Ammonia here is not a hydroxide base, but you do end up with a salt. This is ammonium chloride. Now, if you evaporate the water from this, you will end up with a solid crystalline substance with a high melting point, as you would for any ionic compound. Here's another one where we've got nitric acid in this case and ammonia. In this case, we end up with ammonium ion again, of course, and nitrate ion. This compound here is called ammonium nitrate. That's the famous fertilizer that's also used in things like some kinds of improvised explosive devices and stuff. What do you reckon it is? It's a white, well, you don't know that it's white, but it is. It's a white crystalline high melting point solid. Okay, this one here, the stoichiometry of this reaction, remember that word, stoichiometry, the ratios in which things react? The stoichiometry for this reaction is a bit different than the others. These are 1-to-1. This one's not, because remember, this thing is phosphoric acid. It's actually got 3 protons that can add to a base. So you need 3 of these, because these guys, ammonia, can only pick up 1 proton here. So the stoichiometry is 1:3. You end up with 3 ammonium ions and of course 1 phosphate ion, as this is called here. And the compound, the formula would look like this: ammonium phosphate NH4 in brackets 3, because you've got 3 lots of it, there they are there, with phosphate ion. Remember again, the charges are implied. You've got to be able to figure them out, and the good news is those kind of things are listed in your periodic table. How does all of that work? How does ammonia actually pick up a proton? Well, the answer is it's got 2 available electrons here, and I've drawn them as dots. Why it's got this won't become apparent to you until a much later lecture. But what's happening here is that proton is going from the HCl over to the nitrogen there, which can offer up 2 electrons as a covalent bond. So you end up with a covalent bond, but of course, because this was H+, this becomes a positively charged polyatomic ion. And of course, what's left over is Cl- there. In this case, I actually drew the dot in, indicating that hydrogen had left behind its electron. Okay, naming these compounds, again, you don't have to remember this. This kind of information is actually written in your periodic table and other information. So just so you know though, if you look at a compound like this, HF as a gas, it's actually in the molecular form, i.e. it's a molecule. So its name is hydrogen fluoride. You'll understand more about the ide later. Notice how all these names tend to kind of change to ide. Well, at least for some of these molecules here, hydrogen chloride. But then we go over to the acid. So we're talking about these gases being bubbled through water, like I showed you previously. Then it's HFAQ. So it's then donated its proton to water. It's actually then H3O plus F minus. The name of that solution is hydrofluoric acid. Notice the name change there. For HCl, that's what you buy when you're balancing the pH for your pool. That's hydrochloric acid. So you don't go in and buy hydrogen chloride, or at least I hope you don't, you go into the shop and you actually buy a solution of this that's been bubbled through water, forming hydrochloric acid. There's just a few notes for you there about what's happening with the names there, with the change of suffix to "ic." And again, they're listed in the periodic table and other information. Okay, we're on to the next section, so I'm going to leave it there